Okay, everybody. Welcome back to being in person. I want to go through a couple of quick announcements. First off, in the interest of full disclosure, I know I'm a little behind on emails and whatnot. I was out of town for the past couple of days, and yeah, they just started to add up a little bit, so my apologies on that. One thing I will say is I'm going to have the attendance grades. My goal is to have those updated by the end of the week. I'm going to count everybody present for Lecture 7 because that was virtual, and I'm not going to hold the class to account for not being able to do that in person. And so my policy has generally been that for those days, I'm just going to count everybody present. Homework, my goal is to have the outstanding assignments graded by the end of the week as well, or at least by the next lecture. But all of the outstanding solutions are posted. As for homework 3.1, I'm going to assign that later today. So it should be, it won't show up at 9:30 like the others will, or like the others have, but it'll be posted hopefully by the end of business today. Sound good? Let me just ask a general question before we move on to our next topic, which is torsion. How did the thermal homework go? Was that straightforward? Were there any big ticket questions? I'm just curious. I'll say this, in my experience of teaching this course, the easiest topic on the first exam has, like, of all the stuff we talked about, has been the thermal stuff. It hasn't really been that challenging. So, but I do want to see if that was good. Anybody have any questions? Okay. All right. So today what we're going to do is talk about something completely different, which is this concept of torsion. And the thing about torsion is, so we're changing what we're doing in terms of load and in terms of response. Okay? So what I'm talking about is taking an element and twisting it on each end. That's different than taking an element and yanking on it. Okay? So, and to be clear, the derivation that I'm about to go through, there's going to be a lot of formulas and a lot of equations and a lot of calculus in our derivation I'm about to pull up. It is way different than axial loads. Now the question might be, why are you talking about this now? Like, if we just finished axial loads, why are you going into torsion? Because even though the derivation is way different, even though the response is different, the actual governing equations are very, very similar. The angle of twist versus the axial elongation of a bar are very, very close. So for the first exam, if you're going to lump axial with something else, lumping it with torsion makes a lot of sense. The problems are very similar, the equations are very similar, and so it's not a completely different animal at the end of the day. The derivation's different, but not the end of the road. Now, before we begin, I want to say something right now. So, for axially loaded bars, it didn't really matter what the bar looked like. Now, we had a lot of bars in the class that were circular, and so the cross-sectional area was pi d squared over 4, but it could have been a square bar, it could have been rectangular. It didn't really matter, because the stress was defined as P over A. So as long as you knew what the area was, it didn't matter if it was a circular bar, rectangular, triangular, its cross-section looked like Mickey Mouse, it didn't matter. Okay? But for torsion, that's not the case. Okay? I'm going to say something right now, and then I'm going to explain it later. So for this course, for every problem dealing with torsion, the cross-section will be circular. Every problem. Okay? Now, your question might be, why? Well, there's a couple reasons. First off, the practical reason. And this is probably more towards you mechanical engineers in the room. But I want you to think a little bit about cars, about engines, and think about the elements that are twisted. So steering columns, axles, transmission axles, etc. What do they all look like in your head? The elements that are twisted. More often than not, they should be circular, right? So the practical reason is that in engineering applications, when we twist something, we tend to use circular elements. That's the practical reason, but let's dig into it a little bit more. Why? Why do we limit torsional problems or torsional systems to elements that are circular? The simple answer is because of warping. So whenever you twist a circular cross-section, and by circular I mean a solid shaft, a circular pipe, what happens is, here's the element, you twist it, and it rotates. That's what it does. Anything that's non-circular tends to do something else. Not only does it twist, does it rotate, but it undergoes what's called warping. Warping is when you twist something and it actually deforms in and out of plane. And that's something that isn't really advantageous. If you have, let's say, wheels on either end of this square shaft and you twist it, the ends of the shaft are going to butt into the wheels. And that's not going to happen if the shaft is circular. Okay? So before we even get into the math, and this is largely for you mechanical engineers, if you have an engineering system and you've got something that's twisted, make it circular. Make it a circular cross-section. It's going to be a more efficient response, and it's going to be a more desirable response. Now, for you civil engineers, and this is maybe also true for you biomedical engineers, in most structural systems, well, let me ask you this, how do you think we deal with torsion? Well, in civil engineering, we try and avoid it. We try and develop bridges, buildings, etc., where we reduce the amount of torsion as much as possible. Sometimes it's impossible, and we do have to deal with it. So, for example, whenever you have I-beams in buildings, and the I-beam undergoes flexure, the top of the beam is experiencing compression, the bottom of it is experiencing tension. And things in compression, and we're going to talk about this later in the semester, but things in compression like to buckle. And with I-beams that are being bent, the top wants to buckle, the bottom doesn't. And the beam doesn't really know what to do with that. So when you start getting to that maximum capacity, what happens is the beam sort of kicks out and twists. And there's this mode that we investigate in steel design called lateral torsional buckling. And so there is a twisting phenomenon. And how do you handle that? Well, you have to account for not only just the rotation, the pure torsion, but you have to handle the warping as well. And there are ways to do that. There are warping constants, and we can get into advanced mechanics land with warping functions and energy methods and things like that. But more often than not, in most practical situations, we either use circular elements or we try and avoid it. So I know I'm harping on this a lot, but I'm making a point that we will never have problems, at least in this class, where the torsion is subjected to a non-circular element or a heart-shaped element. So somebody did a heart in the back. Oh my goodness. It's too early. All right, any questions? All right, now I'm going to take a step back and say I got about 20 slides and there's a lot of derivation. So my apologies, okay? But first off, this is already on Blackboard, so if you missed something, it's okay. And I'm not interested in your ability to regurgitate this or repeat this. I don't want you to think that this is something I expect you to do on your own. I'm not interested in you deriving something like this. What I am interested in is your attention, because we're going to arrive at a certain cross-sectional property, and that cross-sectional property is new, okay? For example, when we did axial stress, we found that the stress was computed by taking the applied load over the cross-sectional area, right? And that area was a number. The cross-sectional area is 4 square inches or 6 square inches, and that number is a characteristic that defines what that shape looks like, right? And we've already dealt with section properties before, and you've been dealing with them, at various levels of your mathematical education, your whole, educational career. I'm going to use this as a prop. So, for example, if I was trying to look at the cross-section of this paper towel roll, okay, so for example, I can compute the cross-sectional area, right? pi over 4 times the outer diameter squared minus the inner diameter squared, right? What other cross-sectional properties could define what this shape looks like? Well, there's the perimeter, the circumference, the centroid, right? So these are numbers that define what this shape looks like. And we're going to arrive at another property that is relevant to torsion. We have a name for this property, and I'll admit I use a little bit of a different term than your textbook uses. Your textbook uses I sub P. I use the letter J. I think it's a little easier, but we'll get to that. Okay. So we're going to make a few assumptions regarding the behavior. So when we twist something before and after, the length doesn't change. And when we twist something before and after, if it was a circle before, it remains a circle after. So the geometry doesn't change. And again, that's largely true for circular elements subjected to torsion. So when we, skipped ahead one too many. Okay, so here's the torsional shaft before we apply the load. Here's after, okay? And so if you pay attention to one of these little differential elements, right? So here's what it looks like before. So this is me just sort of painting a little grid on the torsional element before we apply the load. And here's after. This looks a lot like an element under shear, right? Remember when we first defined normal stress and shearing stress and normal strain and shear strain that we said that shear is just a change in angle, right? So what we're going to do is try and find that change in angle, which is the shearing strength, okay? Now, the way I'm going to do that is I'm going to cut out a little disc, and I'm going to investigate what's going on with that little disc. So I'm going to look at a little element inside that disc, this little shaded element right here, okay? So we're going to look at our geometry before and after, and we're going to see if we can isolate some of the parameters that we're interested in. Now, does anybody remember the formula for determining the arc length of a circle, right? Or of a given segment of a circle? So if you have a circle and you're trying to determine that arc length, you take the radius times that angle. Y'all remember that? And so if you did the whole circle, it would be the radius times 2 pi, and that's the circumference of the circle, right? So we're going to see some of that stuff pop up here in a little bit. Okay, so here's that little element in the shaft. This is before. This is after. Okay, so you can see sort of the deformation before and after the applied load. What I'm interested in is this angular change, and that angular change is the shearing strain. That is the strain, and we call that gamma, the little Greek letter that looks like a little y. That is our shearing strain, okay? We're going to see if we can isolate what that looks like, okay? Now, the way I'm going to do that is I'm going to look at this little arc length right here, and I propose that that arc length equals this radius times this angle, or it could also equal this radius times this angle. So I can pretty easily sort of eliminate that arc length, because what I'm interested in is determining the shearing strain. And I propose that that shearing strain can be defined with this. Okay, so rho is the distance from the center of the shaft outwards, right? So that's literally like the radius of the shaft, if you will. And this d phi over dx, that is the rate of change of the angle of twist. So I can relate how much the shaft is twisting to the resulting shearing strain. Now, there's some behavioral observations we can make with this. So let's take a step back. Okay, I want to take our time with this. And again, I'm not interested in your ability to regurgitate this entire thing from start to finish. I just want you to make sure you get the ideas. So, number one, the strain is proportional to the distance from the center of the shaft, right? What I'm getting at is, here's the shaft, and we're twisting it. The farther away you get from the center, the bigger the strain is. So, how much stress and strain so let's just make sure we understand this. If I have a shaft and I twist it, how much stress and strain do I get in the middle? In the direct middle. You're shaking your head, why? None. So that's one thing to keep in mind. When you twist a shaft, the center doesn't see anything. No stress, no strain. So it's also one of the reasons why pipes tend to be pretty common for circular shaft, because the center's not seeing anything. Maybe we don't need that material in the middle because it's not doing anything, right? It's not seeing any stress. It's not contributing to the system, right? So pipes are pretty common for torsional shafts, and that's why. Now, this is telling me that the strain, now I kind of skipped a little bit, but this is telling me that the strain is proportional to the distance from the center. Well, since stress and strain are related, now in shear land, we say that instead of Young's modulus, stress equals E times the strain. For shear, we say stress is G times the strain. G is just another material property. So not only is stress, or it's not only is strain proportional from the center, but stress is as well. Everybody good so far? So here's what I'm talking about. If I have some solid torsional shaft, I propose that the stress looks like this. So here's the center of the shaft, zero stress in the center. But as I get further and further away from the center, the stress increases. So let's think of this behaviorally. I take an element and I twist it. Where is there zero stress? In the middle. Where is the maximum stress? On the outer surface. Now, I want to be clear, this triangular stress distribution is occurring everywhere. You know, like I could draw it right here, I could draw it, right here. It's occurring everywhere. All it's saying is that the further away that you get from the center, the bigger the stress is. So in torsion land and in engineering land, I want you to think about this. So as an engineer, where are you interested in determining shearing stresses? On the outside, right? See, that's a little bit different, okay? And maybe that's another unique aspect of torsion that didn't exist with axial loads. If you take a bar and you yank on it, you get sigma equals P over A. But that's the case everywhere, right? So for example, if this was a circular bar and I yank on it, I get sigma equals P over A, and that stress is here, and here, and here, and here, and here. It's the same stress everywhere, right? But with torsion, that's not the case. Torsion, as an engineer, if the stress on the outside is within limits, then you're good. So that's going to be something that's kind of going to start to creep up. Not just what the stresses are, but where are they occurring, okay? So for example, if I have a beam that's subjected to, let's say, a uniformly distributed load. Y'all remember how to draw moment diagrams? Or y'all remember that from statics? So I can determine where that maximum moment is. Let's say it's in the middle. Okay. But where is the maximum stress from that moment? Well, it's either on the top or the bottom of the beam. How did you figure that out? We'll talk about that later. Don't worry. Well, likewise with torsion, where is the maximum stress from torsion? On the outer ring. So, I propose that a function for stress, tau, as a function of what I'm calling rho. Rho is the distance from the center to how far out. Rho is going from rho equals 0 to rho equals r being the radius of the shaft. That the stress is equal to rho over r times some maximum stress. We don't know what that maximum stress is yet. We will figure that out. The way that we are going to figure that out, and this is kind of a common instance in torsion land or in mechanics land. Did somebody raise their hand a question? I thought I saw. So the way that we determine this in mechanics land is what we're going to look at are the forces along a given element of the cross section, and then we're going to integrate. Okay. So I'm going to look at a single circular ring. So what is the area of this little ring? Well, the area of that ring, I'm going to say, is the circumference times the thickness. The thickness is some little differential element d rho, and the length, or the circumference, is 2 pi times the radius. So this is the area. How do I determine the force? Well, the force is the stress times the area. And how do I determine the torque or the torsion? It is the force times the distance, right? What is the definition of moment? Force times a moment arm. And so I'm going to say force times some moment arm. What I'm then going to do, I'm going to integrate this to get an expression for torque, take that, set it equal, and solve for the stress. That's what I'm going to do. So there's going to be a lot of calculus popping up. That's kind of the end game. Everybody with me so far? So, here's our expression for stress. Here's our area. Here's this expression for force. So the expression for force, stress times the area. Plug in my expression for stress. Plug in my expression for area. Shut that out. Expression for torque. Now what I'm going to do, I'm going to take this torque expression, and I'm going to integrate it. Again, I'm not hyper concerned that you follow every single calculus step. That's not really what I'm interested in. I just want you to get the concept, if you will. Everybody with me so far? Now, the point I'm making is I kind of want to look at what's going on inside that parentheses. What's going on there? I've got 2 pi times an integral from rho equals 0 to rho equals r of rho cubed dp, or d rho. Everything inside this integral is a section property. It has nothing to do with the applied loads or the stresses or the strains. This just has to do with the circle itself. If I were to evaluate that integral, I would get a numerical value which characterizes what this cross-section looks like. And we call that integral and that cross-section J, or that cross-sectional property J. So, again, I'm not worried that you follow every single calculus step, but what I want you to recognize is that we've used basic statics, definition of forces, definition of moments, integrated about the property, and we've isolated this. And we get this property called J. That term J is a cross-sectional property related to torsion. Okay? So I propose what we can do is, if we know what J is, right? If we know what J is, we can determine maximum stresses because we now have a function for our stress. We can determine maximum strains, etc. Let's talk about J. I swear I hit this button. J is what I'm calling our new section property. I'm calling it the torsional constant. Just like A, cross-sectional area, that is a section property. J is a section property as well. Now the way that you compute that is you take 2 pi times the integral of rho cubed from rho equals 0 to rho equals r. The beauty of this is actually a pretty simple integral, so we can just sort of carry this out right now. So for a circle, J, this is after you chug it all out, J is computed as pi r to the 4th over 2. So that's how you compute J for a circle. If you wanted to determine it for a pipe, you would just say J outer minus J inner. So, and don't worry, I have a little slide here at the end that summarizes all of the formulas, in one. Hey, here it is. So it is very easy to determine J for pipes as well as J for circular shafts. I seem to remember, I think you asked a question in statics. You said, wait a minute, we have this IX, we have this IY. What is this IP, or what is this IXY in statics? What's this other property? That's what it is. I think I remember telling you in statics, I said that you're going to see this again for torsion. Well, here it is. You're seeing it again.
That was like 3 months ago. He makes a good point.
I don't even know what I ate for breakfast.
I didn't.
You said I don't even know what I had for breakfast today? I guess I have a good memory. So, now that we have this term for J, remember we can relate stress and strain. So we have, now we have a function for stress, we have a function for strain. We can determine maximum strains. If we wanted, we could integrate this to determine the angle of twist. So this is just me carrying out the integration along the length to determine the angle of twist. Before, it was a little fuzzy because we didn't have J. Now we can carry this integral out pretty explicitly, and it's pretty straightforward. I really want to take a second and focus on this expression right here. So, first off, let's look at this. This is the angle of twist. This is sort of the money, if you will, at the end of the day. The relationship between the applied load and the resulting deformation. Remember, what's the name of this class? It's Mechanics of Deformable Bodies. So, this is telling me the angle of twist is TL over GJ. So, let's take each of those four properties. What's on top? An applied load and the length. What's on the bottom? Material property, cross-sectional property. I'm going to break out the chalk. How did we determine the axial elongation of a bar? Applied load, length, material property, cross-sectional property. Start to see why we're doing torsion right after axial loads, because there is an analogy to the math that we do and to a lot of the problems that we solve as well. Now, what if we need to integrate? What if the torsion changes as a function of the length? What if the cross-section changes as a function of length? Well, how did we do that before? We basically just integrated this from 0 to L. And if that was a function or that was a function, we just integrated it. How's that any different from this? Same story. Make sense? So, this is the money slide I was telling you about. If there's anything to write down, it would probably be this. Because this has all of our stress formulas, strain formulas, deformations, and the J formulas. Now again, in the textbook, they call it I sub P, but they're the same. The other thing I will mention is that while you're writing this down, and I'll use the J shaft to explain this. So when we did our derivation, we got J as pi r to the fourth over 2. That is also equal to pi d to the fourth over 32. Why the 32? Well, because it's to the fourth, right? So 2 to the fourth is 2 times 4 is, or 2 times 2 is 4, times 2 is 8, times 2 is 16, right? So if you're going from pi r to the fourth to pi d to the fourth, there's a 16 in there. So pi r to the fourth over 2, or pi d to the fourth over 32, 16 times 2. Does that make sense? But the one thing I want you to realize is how analogous this is to axial loads. What does change from axial loads is that when you apply an axial load, the stresses and strains are constant along the cross-section. With torsion, they are not. With torsion, we get this. We get the stress and strain increases as you go from the center. So at the center, stress and strain are 0. Stress and strain increase from the center. Does everybody have all this? Give me wait. I still see some folks writing. Are we good? Now, I have a couple more. So, probably the most important one is actually this one. A lot of times with materials, you are only given an explicit set of properties. Now, there's a graduate course being taught next semester called Theory of Elasticity. It's one of my favorite classes when I was in grad school. And you learn about 3D stresses, 3D strains, and all sorts of crazy stuff associated with that type of math. And one of the things that you learn is that you could compute just about every elastic material property that you need for real deal stress and strain analysis with only two numbers, E and Poisson's ratio. Everything else is a function of those two in the elastic range. So, for example, a lot of times on torsion problems, I might just give you E and rho, but you need G because G is the shear modulus that relates shear stresses to shear strains. That is easy to compute. It is just E divided by the quantity of 2 times 1 plus nu. It's really easy to do. I'm just telling you that now so that you have that. We're actually going to do that for our first example. Very good? All right, we got two problems, and for you mechanicals, one's in US units, one's in metric, so you're welcome. The first one just has a single torque applied. What we're going to do is we're going to look at a couple different scenarios. So, number one, I'm going to say, okay, if I just gave you the torque of 250 foot-pounds, what's the maximum shear stress in the bar? What's the angle of twist? This is a pretty direct, straightforward problem. The second one maybe takes a little bit of thought. So the second one says, if I told you that the maximum allowable shear stress is 6,000 psi and the allowable angle of twist is 2.5 degrees, what's the maximum permissible torque? That one takes a little bit of thought. One thing I do want to show you is some notation. And that's kind of why I like this image. Does everybody see what's going on here with this torque? See how there's two arrows? Y'all remember how we described moments with the right-hand rule, right? So if you have your right hand, the thumb is pointing that way, then your fingers tell you which direction the moment curls, right? So this is saying that the torque, I'm taking this bar and I'm twisting it this way, right? And this one is saying I'm twisting it this way. So I'm doing this to it. Does that make sense? So I'm taking it and I'm doing that. So I'm twisting it, applying that torsion. That notation is kind of important. Make sense? All right. I'll just talk a little bit about the next one. The next one, I have a shaft that's subjected to multiple torques. And we're basically just going to determine the maximum shear stress in each part and the angle of twist. This one's actually maybe a little bit more conceptually straightforward, but there's a lot more going on, so there's more parameters. Okay. Does everybody have all this written down, or do I need a little bit? Let me give you a little bit. Okay. All right. So we have a 54-inch solid circular steel, or a solid steel circular bar, and it has a diameter of 1.5 inches. So let's see. So we have L is 54 inches. We have G is 1.5 inches. Now what's new is this property J. So J is pi over 32 d to the 4th. what's this come out to be? And we'll say 3 decimal places. Second. Did I second me on that? All right, here we go. Your engineers, you should have your Casio FX115 ES Plus or similar scientific calculator at the ready. There we go. Now, we were also given E. Is that, and Poisson's ratio is that. So this is also the new one. We're going to compute G. And tell me what we get here. And we're engineers, so we'll say like the nearest PSI. We don't need to get crazy with it. So like the nearest whole number. Remember, this is just the slope of the curve, so it's a high number, but that's okay.
11,153,846.15.
That's it. We'll go with that. Second, yeah. So the AISC Steel Construction Manual, just to give you some perspective on accuracy, we're going to use this number, but the Steel Construction Manual just uses 11.2. So just to give you an idea on what's good enough. Come on. Okay, so we'll call this A. Call that B. So part A says, what is the maximum shear stress in the bar and the angle of twist if the torque is 250 foot-pounds? This is easy. This is really, really straightforward. Okay? So the torque is 250 foot-pounds. Now, anybody see something we ought to do with this? There you go. There's everything up here. Inches, 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 pounds, inches. So, now what do? Do I divide it by 12 or do I multiply by 12? There you go. So 250 times 12, 3,000. It's exciting, I know. So, what we're trying to determine is Talmax and the angle of twist. Now, Talmax, pretty easy. TR over J. Remember, this is a solid circular shaft. Right? Which means the maximum stresses are on the outer surface, the outer extreme fibers. By the way, if you ever hear me use the term extreme fiber, that's what I'm talking about. So if I'm talking about the circular shaft that I twist, the extreme fiber is the outer edge. So TR over J. So what's R? Well, what's the diameter of the shaft?
1.5 inches to the diameter, so 0.7.
Boom.
PSI.
Do I have a second on that? Do I have a second on that? Come on, everybody. Was that good? Is that, yeah. Okay, I'm getting people shaking their head, yes. Okay. The angle of twist, again, torque, length, G, J. Now, I'm going to go ahead and tell you, when you compute this, you're going to get a really small number. That's okay. Trust me. Because we're going to talk about that number here in a second. But trust me, it's really small. My nose is itchy. All right, okay.
That's an average number, it's not that small.
But now hold on. We're going to stop for a sec because I want everybody to pay attention. Eyes up here. Eyes up here. All right, so Talmax, inch pounds times inches gives us pounds and square inches up top. So if we divide by inches to the fourth, we're left with pounds per square inches, or PSI, which makes sense. We're looking for stress, right? What's going on with units here? Okay, what do we have on the bottom? PSI times inches to the fourth. So that's going to leave us pounds times inches squared. Here up top, inch pounds times inches squared. So pound inches squared on the top, pound inches squared on the bottom. The units cancel. So this is an angle of twist. I'm asking you, what are these units? Say it again. Somebody said that. Well, okay, hold on.
Is 1 over inch to the fourth? No, it's 1 over square inch.
No. Degrees. All right, hold on. Watch. So, inch pounds times inches on top, pounds, inches squared times inches to the fourth. So,
Would it be
Pound inches squared.
wait. Who said that? All right. When you have an angle that's unitless, what's it in? There we go.
I'm close.
I was close.
I mean,
I didn't do the
I
conversion.
kind of said that.
So, if this is in radians, how do I convert it to degrees? What is that?
1.67 degrees.
So yeah, so the angle of twist expression is by default out our answer as a unitless quantity because it's an angle, and mathematically, dimensionless angles are in radians, okay? So when we go to our second question, we're going to have to take that into account, okay? Excuse me. Let me. Oh my Lord, it's too early. Okay.
Yeah.
It's too early for this. That's on you. All right. Let me stop for a second. In all seriousness, I want to stop and see if this made sense. Okay. So now what we're going to do is we're going to talk about the second part. And the second part, I think each component is easy, but the decision requires some thought. So if the allowable shear stress is 6,000 psi and the allowable angle of twist is 2.5 degrees, what is the maximum permissible torque? So what we're going to do is we're going to take each of these one at a time. Okay? So let me show you what we're going to do. Let's take the first one. So let's start off with this. So if I told you the allowable stress was 6,000 psi, how would you determine the maximum applicable torque? Well, let me see something. How do we determine Talmax? We just did that. How do we do it? Do we know J? Do we know R? So if I said if this is the maximum allowable stress and we need to determine the torque that will generate that stress, what do? Solve that equation for T, right? So therefore, come on, this isn't too bad. Just solve for T. Actually, let me rewrite that and say allowable. What is that?
I third.
3,976. Hold on. Now, wait. What are the units? What are we solving for? A torque. There you go.
Let's go, baby.
You're getting very excited about torques. You're getting very excited about this. But this is a very
8 a.m. in the morning.
time and units. All right. So
being extra precise.
Okay. All right. All right. So I want to be clear on what we just solved for. If I have a limiting stress of 6,000 psi, then the maximum amount of torque I can apply is 3976 inch-pounds. So this is me twisting that thing. Once I hit this, no more. If I put more torque than that, I'm going to generate more stress than 6,000 psi. Why would that be bad? Well, if I exceed this stress, I might fail the shaft. If I fail the shaft, then the system fails, car explodes, all that. We don't want that to happen. Sound good? All right. Now, what was the other part? What's the other part of the problem? So if the allowable shear stress is 6,000 psi, what's the maximum permissible torque? And if the allowable angle of twist is 2.5 degrees, what's the maximum permissible torque? So let's talk about that. Now what I'm going to do right now is convert that right now. I don't want unit problems.
40436.
Is everybody okay with that? Now, how do I determine the angle of twist? What's the formula?
I equals TL over GJ.
Okay, so this is my angle of twist. I know G, I know J, I know L, so take this, divide, and I can solve for the torque that would generate that angle of twist. Does that make sense? Okay, so now we have another Tmax. Does that make sense? So that's just me taking this equation, multiplying both sides by GJ, dividing both sides by L. Everybody okay with that? So a little bit.
J is just going to be 497.0.
Oh, thank you. You are 100% correct.
inch pounds.
4479.2, and those are inch pounds. So 44. Do I have a second on that?
Is that 0.0436?
Yes. So, well, first off, do I have a second on this? Okay. All right. Let's recap a little bit. What have we done? If the maximum stress is 6,000 psi, then the maximum allowable torque is 3976 inch-pounds. On a separate note, if the allowable angle of twist is 2.5 degrees, that's the maximum permissible torque, 4479.2 inch-pounds. But that's not what the problem asks. What the problem asks? If the allowable shear stress is 6,000 psi and the allowable angle of twist is 2.5 degrees, which is the maximum, what is the maximum permissible torque? So the question is, which one of these is the allowable torque? The smaller one, which in this case is this. Why? Let's assume that this is the correct answer. So if I put this much torque, it will twist at 2.5 degrees. But if I put this much torque on the system, how much stress am I going to get? More than 6,000 psi, right? This value ensures that I achieve, maintain both limits, right? But if I pick this one, I'm going to violate the stress limit. So it's the minimum. In engineering land, we say that this governs. Or I do kind of like foot-pounds for torque. We're going to do some problems later on involving power-torque relationships. So if you have an engine that needs to supply 150 horsepower, how do you relate that horsepower to torque? And we have a conversion where we can relate horsepower to foot-pounds. So we'll stop for a second to see if this makes sense. Anybody has any questions? Or did I go too fast? Or I need to go back to the other sheet. All right. We have a circular pipe subjected to torques. So again, pipes are very, very common for torsional elements because again, the center of the pipe, or the center of a solid shaft experiences no stress or strain. So from an engineering perspective, why put material there? I can save money by removing that material since it's not doing any good anyways. But you can't make the pipe too thin. So let's, off the side, let's talk a little bit about that. If you had a torsional shaft, it doesn't make sense to put material in the center because it's experiencing no mechanical stress. But that doesn't mean the pipe should be infinitely thin either. There are reasons beyond torsion where we might want the pipe to have some beefiness to it. Maybe we need to consider thermal considerations. Maybe we need to consider corrosion protection. There actually needs to be some thickness to the material. So I know that's off to the side, but just wanted to say it. We have an outer diameter of 40 millimeters, a wall thickness of 5 millimeters. We've got 3 torques applied, so we're going to have to break out some cross sections, some section cuts, and what have you. We have the following torques that are applied. Now the torques are driven, the shaft is driven by gear C. So what that means is, if you look at the image, gear C is supplying a torque of 450 Newton meters, and it's supplying it, if you follow your right-hand rule, it's supplying it like this way, so here's T2, and that torque is going this way. T1 and T3 are acting in the opposite direction, right? So T2 is driving the shaft, if you will, and then T1 and T3 are opposing it. And if you add up T1 and T3, what do you get? So you have 450 going this way, this and this going the other way. How much is that? There's 450, right? So 450 is going this way, and it is being opposed by 450 going in the opposite direction. So the sum of torques are 0. It's static. Does that make sense? Or we can consider this a static scenario. We've got our lengths, got our shear modulus, etc. All right, before we start chugging out some examples, I want to talk a little bit about units in SI land. Number 1. Does anybody remember that? Take a kilonewton over a millimeter squared. What do you get?
That's a gigapascal, right?
There you go. Here's another one. Did you know that a Newton meter is the same thing as a kilonewton millimeter?
Multiplying 1 by 1,000 and dividing the other by 1,000.
There you go. You're multiplying one by 1,000, you're dividing the other by 1,000. So the point I'm making is this. Look at the data we were given for the problem. It looks like a unit's nightmare because we got gigapascals and millimeters and meters, but look at the torques. The torques are being given in Newton meters, which are the same thing as kilonewton millimeters. And this is kilonewtons over millimeters squared. So actually all the units are already consistent. You see what I mean? So we don't have to go into crazy units land. So for you SI fans in the room, you know, there you go. All right. We were given that the pipe has an outer diameter of 40 millimeters and a wall thickness of 5 millimeters. Now, keep in mind, we're trying to determine J for a pipe. Anybody have that formula handy? What are we missing? So how do we determine DI? Wait, say again?
DO minus T.
All right. DO minus T or 2T. Because this is a good point. Here's the pipe. This is D naught. This is DI. And so how do you get to DI from D naught? You got to take off one of these and one of these. So two thicknesses. Does that make sense? That's a really easy thing to make a mistake on. That's really easy. Yeah. I'd argue, so radius. There you go, right? The inner radius is the outer radius minus one thickness. That makes sense? I can do that one in my head.
I second you as well. I've done my best.
I have been called many things. Fancy's not one of them. So
You're dressed up nice today. What you talking about?
this was a free polo because it's got the college logo on it.
Man, they giving that stuff out?
Might have gotten these from like Walmart. I don't know.
If they're giving out free drift, take it.
I'm learning so much lingo from you, sir.
At least you learned something from me. I'm gonna show up to the next Weisberg conference. Yeah, t-shirts.
Yeah, y'all should give out more t-shirts out of that dean's office.
Yeah, you should bring that up to the person.
Yeah.
What do we got for this now? Hey, let me, in all honesty, let me say one thing. So we are taking these and raising them to the fourth, but we are also dealing in millimeters to the fourth. So before we had a really small number. Because we're dealing with millimeters to the fourth, this might be very big. That's okay. So we'll say like to the nearest millimeter to the fourth, because it's kind of a big number. Yes, I'm ready.
171806.
Second.
Oh, that's huge.
Okay, everybody, all right. So what we're doing is we're basically taking an area times a distance squared. So there's your diagram. Now, J is 171,806 millimeters to the fourth. Don't forget we have we were given G is all right, let's talk a little bit about equilibrium. So I'm going to idealize, here, let me move this like over here. So here's the shaft. So we're going to say here's the shaft. I know it seems like we're running short on time, but we got time to do this one. So I've got, let's see, T1. I've got T2, T3. Does everybody see how I'm doing that? Everybody see that? So notice the direction in which I have these segments drawn. What we're going to do is we're going to essentially cut sections to determine the internal torque inside each segment. So here's our segment, right? And we're going to cut a section. Oh, come on. Did you do this to me? Hold on. I might have to close this thing and open it back up.
Dr. Mike, did you get an 80 GPA? That's impressive.
Caffeine would help you, sir. That's all I'm saying. Okay, so what we're going to do is we're going to cut a section. Now, for section 1, what I'm going to do is I'm going to cut, well, actually for both of these sections, I'm going to cut a section and look to the left. So if I look at section 1, this is what I've got. Now, notice how I'm ignoring sort of reactions at the end, because I can tell you those reactions are 0. Remember, T2 is like 450 to the right, and T1 and T3 are both also 450 to the left when you sum them up. So there is no torque reaction at the end, right? So there's an internal torque right here, which we'll call TBC. And so this T1 is 275 kilonewton millimeters. So if I treat this like a sum of torques equals 0 problem, then TBC is like that. Whereas if I cut section 2, Then I've got T2 right here. For 50. And here's my section cut. But now I've got TCD. And so if I sum torques, what do I have? Well, do I have it drawn in the correct direction? Actually, I don't think I do, because I've got 275 this way, 450 this way. I need another 175 going this way. This is actually the wrong direction. And that's going to be like that. Does that make sense? So, let's ask a couple questions, okay? It's the same shaft across the board, right? Like it's not like the shaft gets any different. It's not a different size shaft from one side to the other, right? So, how do I determine maximum stress? What, TR over J? Both segments have the same J, right? And both segments are going to have the same R, right? What is R for this shaft going to be? What's the outer diameter? So the same R and the same J. So which shaft experiences the bigger stress? BC or CD? Well, the bigger torque, right? So if I wanted maximum stress, I'd just say TBC R over J. And since we're running short on time, I'm going to do this one myself. So when you chug this out, you're going to get, I think we said this was 6. 806. When you chug this out, you're going to get a very small number. It's like 0.032 gigapascals. But remember, we can convert that to megapascals and say Talmax is that. Okay? And the final thing that I will say is that the problem is also asking for the total angle of twist. The total angle of twist from point B to point D. And so the way that you do that, I don't want you to think that's really complicated. All it is the angle of twist from B to C plus the angle of twist from C to D. And so all you're going to do is say TBC, LBC over GJ plus TCD, LCD over GJ for the other shaft. The only thing to keep in mind is that this shaft experiences a torque this way, and this shaft experiences a torque in this way. So what you're actually going to end up doing is not adding these two, but you're going to subtract them. See, when you chug this out, what you get, and again, at this point it's just plug and chug, is you get 0.0100 radians this way, plus, and over here, you get 0.0051 radians this way. So what you end up doing is you subtract them and you say that that is 0.0049 radians that way, or 180 over pi, 281 degrees. My apologies for that going like a little bit over, but does that make sense? I don't think that's all that complicated, especially after the last example we just did. I think that first example is actually tougher than this one. Everybody good? Well, everybody have a good weekend. I will see you on Tuesday. And I know there was a couple people that came in late. I'll pull up the QR code.